You move $100 from account A to account B. The database subtracts the money from A. Then, before it adds the money to B, the machine loses power. What should happen when it restarts? The answer cannot be probably fine. Either both changes happened or neither did. And while that transfer is running, another request might be reading the same accounts or trying to spend the same money. This is the problem a database transaction solves. But begin and commit are only the control buttons. Underneath them is a coordinated system of private versions, locks, a write-ahead log, and a very precise commit point. Once you can see those pieces moving, transactions stop feeling magical. Start with the transfer as two updates. Subtract 100 from A, then add 100 to B. A transaction wraps those statements into one logical unit, but it has to solve two different problems. Atomicity is about failure. If the process crashes halfway through, the database must not preserve half a transaction. Isolation is about concurrency. If two transactions overlap, neither should observe a state the chosen isolation level forbids. Those are related, but they are not the same mechanism. Durability joins the picture after commit. Once the database reports success, the result must survive the failures covered by its durability guarantees. Consistency is the application and database constraints that every valid, committed state must satisfy. That is ACID. But the useful mental model is simpler. Private work, controlled visibility, durable evidence, then one public decision. Imagine transaction T1 starts the transfer. It reads account A, calculates the new balance, and writes an updated row. That does not mean every other transaction instantly sees the new value. In a system such as Postgres, updates create new row versions. Each transaction reads through a visibility rule, often described as a snapshot, to decide which versions are visible to it. The old version can remain available to readers whose snapshot still needs it, while the new version belongs to the updating transaction until commit makes it visible to future snapshots. This is multi-version concurrency control, or MVCC. Readers and writers do not always need to stand in one single file line. They can sometimes work against different versions of the same logical row. But MVCC is not permission for conflicting writers to ignore one another. Two transactions trying to update the same row still need coordination. One may wait on the other, and deadlocks are possible when transactions acquire resources in opposite orders. So there are two layers. Versions answer, "What may I see?" Locks and conflict checks answer, "What may I change safely?" Now T1 has produced new versions for both accounts. Perhaps those changed pages are still only in memory. If the machine crashes, memory disappears. Writing every changed data page to permanent storage at each commit would be painfully expensive. A page might be much larger than the tiny change inside it, and one transaction may touch many pages scattered across disk. Databases use a different rule. Record the change in a sequential write-ahead log before the changed data page is allowed to reach durable storage. The log is evidence. It describes enough history for recovery to reconstruct committed work. Because the log is append-oriented, the database can make the critical, durable write more efficiently than flushing every data page immediately. The ordering is the important part. Log first, data page later. That is write-ahead logging, or WAL. The data pages can now be written in the background. They may reach storage before or after nearby transactions. Correctness no longer depends on those pages being perfectly synchronized at every instant because recovery has the log. So what does commit actually do? At a high level, the database appends a commit record to the transaction log and makes the required log records durable. Only then can it safely tell the client that the transaction committed, assuming fully synchronous durability settings. That durable commit record is the line between recovery may discard this and recovery must preserve this. Notice what did not have to happen first. Every modified table page did not need to be flushed to its final location. The log became durable first. The slower page writes can follow. Real systems optimize this boundary. Several transactions may share one physical log flush, a technique called group commit. And some databases offer asynchronous commit modes that return earlier, trading a small window of durability for lower latency. So, commit is not merely the last line of your SQL block. It is a storage ordering protocol, and its guarantees depend on configuration as well as syntax. Now, pull the power at 3 different moments. Crash before the commit record becomes durable. T1 was never committed. Its partial work must not become a valid public result. Crash after the commit record is durable, but before all changed data pages are written. Recovery uses the WAL to restore the committed changes. Crash after both log and data pages are durable. Recovery may have little to do for this transaction, but the same rule still classifies it correctly. A checkpoint gives recovery a more recent place to begin. It records progress so the database does not need to scan its entire history from the first day it existed. Different database engines implement recovery details differently. Some logs contain physical page changes, some logical operations, and some a mixture. Some systems redo committed work and undo incomplete work. Others use version visibility, so incomplete versions simply never become visible. But the central idea survives. The log turns a crash from an ambiguous half state into a deterministic recovery procedure. Atomicity is not the absence of partial internal work. Partial work absolutely can exist. Atomicity means partial work cannot become a valid committed outcome. While T1 is transferring money, transaction T2 wants to calculate the combined balance. At a weak isolation level, T2 might observe A after the subtraction and B before the addition. That is an inconsistent view of the transfer. SQL isolation levels describe which concurrency anomalies the database must prevent. Read committed generally gives each statement a view of data committed before that statement began. Run the same query twice in one transaction, and newly committed rows may appear the second time. Repeatable read keeps a stable transactional view in systems such as Postgres, so repeated reads do not drift in the same way. But the exact guarantees behind a level name vary by database engine. Serialization aims for the strongest illusion. The outcome should be equivalent to some serial order, as if the transactions ran one at a time. That does not require the database to literally run them one at a time. It can execute them concurrently, detect a dangerous pattern, and abort one transaction. That abort is not the database failing. It is the database refusing to publish an outcome that could not have happened in a valid serial history. Your application must be ready to retry. Suppose 2 doctors are on call. The rule says at least one doctor must remain available. Transaction T1 reads both rows, sees 2 doctors, and takes Dr. A off call. At the same time, T2 reads the same starting state and takes Dr. B off call. They updated different rows, so a simple same row write conflict may not stop them. Each transaction individually saw a valid starting state. Together, they leave nobody on call. This is write-skew. It reveals why my updates are atomic does not automatically mean my business invariant is safe. You can prevent it by designing an explicit lock around the shared invariant, by changing the schema so the constraint is enforced in one conflict point, or by using true serializable isolation and retrying serialization failures. The important question is never just, do I use transactions? It is, which observations and invariants must remain valid while transactions overlap? When you design transactional code, walk through 5 questions. First, what is the logical unit? Keep every state change that must succeed together inside the same transaction. Second, what can run concurrently? Name the rows, ranges, or invariants that competing requests might touch. Third, what isolation level actually protects those invariants on your database? Do not trust the label alone. Read that engine's behavior. Fourth, what can abort? Deadlocks, serialization failures, timeouts, and connection loss are normal operational outcomes. Keep transactions short and make safe operations retriable. Fifth, where does the transaction boundary end? A database rollback cannot unsend an email or withdraw a message already published to another system. For cross-system side effects, patterns such as a transactional outbox record the intent in the same database transaction, then deliver it separately and idempotently. Now the whole system fits on one timeline. Private versions hold tentative work. Locks and conflict checks control interference. Wall creates durable evidence. Commit makes one public decision. Recovery honors that decision after a crash. Isolation decides which concurrent histories are legal. That is a database transaction, not magic and not just two SQL keywords. It is how a database turns unreliable hardware and overlapping requests into a result your application can trust. If this mental model finally clicked, subscribe. Next time you write begin, remember what the database is coordinating underneath it.